consider this example now. So imagine the differential equation. This y plus a half x dy by dx equals 1 over x. If we differentiate y, we get dy by dx. If we differentiate a half x, we just get a half, but there's no half here. So it's not exactly the derivative of that. But what we can notice is that if we multiply by x, we get xy plus a half x squared dy by dx equals 1. So now we've got a function, y, and its derivative over here. And over here we've got another function, and if you differentiate that, you get x. So it's just like that product rule. First differentiate second plus second differentiate first. It's got that same form. So this is just the derivative of our two functions, a half x squared and y, and that's equal to 1. So if we integrate both sides with respect to x, half x squared y equals x plus c, and so y equals 2 over x plus 2c over x squared. That's our general solution. Great. You can have a go at exercise 7a in the main textbook, which has a lot of practice questions on noticing that you can use the product rule in the reverse to do that. Now, it's actually possible to make any differential equation of this form, dy by dx plus some function times y equals some function that's in terms of x. If you have a differential equation of this form, it is possible to multiply the whole equation by something, a function, to make it so that you can always use the product rule in reverse. So we're going to look at how can we find a function that we multiply all of this by. So times this by that function, times this by that function, times this by that function, so that then you can use the product rule in reverse, like we did up here, and then write in this form to then solve it to get our general solution. So we're going to derive how we can actually go about finding that. Just before you do that, just to make sure you understand what this here means, your differential equation could be dy by dx plus your px could be sine x, y equals, and your gx could be x squared, for example. So you've got two functions, okay, and we're going to look at what we can multiply by to be able to change this into a form where you could then use the product rule in reverse, kind of like what we did over here. Our first step here was to multiply by x. We multiplied everything by x, and then it suddenly became into a form where you can then use the product rule for differentiation in reverse. Right, so normally px and gx would be given to you, so we were just generalizing that and coming up with a way to find out what we have to multiply by. So let's suppose the function we need to multiply by is f of x. We multiply everything by f of x, and then it becomes f of x dy by dx plus f of x p of x y equals f of x g of x. Now, we're only really concerned with the left-hand side. We want to make this into a form such that it's a function. So let's just call it big F. A function times dy by dx plus the derivative of that function times y. Because the y and dy by dx are fixed in here. We want this part over here to be the derivative of this part over here. So let's see what happens if we use that as a condition. So if we say that f dash x has to be equal to f of x p of x, and then we try and find out what f of x is. Let's collect these functions together. So f dash x over f of x. What we're trying to do is find out what this f of x function needs to be, the function we multiply by, to make this into the form in which you can use the product rule in reverse. That's what we're trying to find. So we're trying to find out what f is here. So what if we get all the f's onto one side like this, and the problem here is that we've got the derivative of f. How can we get rid of that? Well, we can integrate both sides with respect to x. If we integrate this side with respect to x, it's the integral of px dx. So in basic terms, it's the integral of the function that was next to your y in the original equation. And if we integrate the right hand side, the integral of f dash x over f of x, that should look familiar. There's a rule associated with that. The integral of f dash x over f of x would be ln f of x. So the integral of px dx is equal to ln f of x plus c. And now you don't have any f dash there. We can actually rearrange this to find out what f of x is. We can find out what function f of x is. And just to remind you, why are we finding f of x? Because f of x is a function such that if I multiply my differential equation by it, like over here, multiply by f of x, multiply by f of x, multiply by f of x, my differential equation will become in the form of the product rule. So first differentiate second plus second differentiate first. It will become into that form. Right, so let's find out what f of x is. To do that, we are going to e both sides. So it becomes e to the integral of p x dx equals e to the ln f of x plus c. That c is in the power as well. The left hand side stays the same, e to the integral of px dx. We can't cancel the e and the ln because there's no ln on the ln is only on the f of x, so we're going to split this up. So it becomes e to the power of c, e to the power of ln f of x. Now we can cancel the e and the ln, so the left hand side is still e integral of px dx equals e to the power of c. Let's just call that a, so some constant a, and the e and the ln cancel out. That's f of x. Actually, we don't need the plus c either, because you've still got an integral on the left hand side that's going to have plus c as well, so we can just leave the constant out, which would make this a lot simpler, because we can collect our constants together in that integral. So f of x ends up being e to the power of the integral of px dx. So we found a way to get a function such that if we multiply our differential equation by it, the differential equation will become in the correct form to use a product rule in reverse, just like over here. In this question, we had a differential equation. We couldn't see the pattern, first differentiate second plus second differentiate first anywhere, but if we multiplied by x, we could see that pattern. You've got your first function here, and this is the derivative of your second function, and this is the derivative of the first function, and this is the second function. So if we then write that down, Well, the order's a bit messed up, but it would be a product of these two functions. Okay, and we did that by multiplying by a suitable function. So now the suitable function that you multiply by to make any first order differential equation of this form into the correct form to solve it is this. And this is known as the integrating factor. So let's write that down more formally. To solve an equation, or ODE, of the form dy by dx plus p of x y equals gx. So something of this form where you've got dy by dx first plus some function times y. Find the function which is e to the integral of px dx. So in basic terms, the function that is next to your y, you need to do e to the power of the integral of that to find the function which you're going to multiply by. This is known as the integrating factor. So you find this, then multiply the ODE by it. Okay, instead of saying it, let's call this the integrating factor. So multiply the ODE by the integrating factor. So if you do that in this case, let's see what happens in this general case. So what we would get is e to the integral of px dx dy by dx plus e to the integral of px dx times px y equals gx. Now what you should notice is that if you differentiate e to the power of integral of px dx, you get the same thing, so just like here, but you have to multiply by the derivative of the function that is inside it. And what's the derivative of that? Well, if you differentiate it, the integral sign disappears, you're just left with p of x. So this whole thing is actually the derivative of this. And you've got a y here, and dy by dx is the derivative of that. So you've got that situation where you've got first differentiate second plus second differentiate first. So it's a product rule in reverse. We can then go on to solving this then. So what are the two functions being differentiated? Well, it's e to the integral of px dx and y. And on the right hand side, I forgot to multiply by e to the integral of p dx. I'll do that now. And that stays like that. Now, normally in questions, it would work out to be usually it's a nice function it works out to be. We'll have a look at that now. Right, so let's put it into practice by trying it with a question. So imagine we want to find out the general solution. Find the general solution of x dy by dx plus 2y sine x equals cos to the power of 4x. Right. Now, just scrolling up a bit, we've seen that to use this method, the equation has to be on this form. So that's the first thing you want to check. Is it in this form? Look at it and look at what we have down here. Hopefully you'll notice there's an extra x next to the dy by dx. So first you have to divide by x to get it into the same form as this over here, which we have learned how to solve. So dy by dx plus 2 sine x over x y equals cos to the power of 4x over x. So I've divided through by that. So now that it's in the correct form, this function next to the y is like our p of x. This function over here is like our g of x from what we stated above. We're now going to do the process to be able to solve this. So we've already seen that obviously like this isn't in the correct form where you can use a product rule in reverse. Therefore we have to use this method. So we're going to find the integrating factor. The integrating factor by definition is e to the power of integral of px dx. Px is the function next to the y, so that's 2 sine x over x dx my apologies, the question was actually cos x over here. Okay, so if we just go back and change that, it's going to be divided through by cos x. So the integrating factor is going to be the integral of 2 sine x over cos x dx. Sine x over cos x is tan, so that's e to the integral of 2 tan x dx. You can look in the formula booklet for this, or you can use the reverse chain rule. You can see it's a function and its derivative, so you know it's going to be ln minus ln cos. But we can look in the formula booklet and see that it ends up being e to the and the integral will be 2 ln sec x. Now 2 ln sec x isn't really helpful because it's still quite complicated, so we're going to move that 2 to the power, so it becomes e to the ln sec squared x. And now the e and the ln cancel, that's just sec squared x. So our integrating factor is sec squared x. So how do we use this integrating factor? We multiply our whole equation that we have by sec squared. So the one in the correct form, we're going to multiply it by our integrating factor. So if you multiply by sec squared, you get sec squared x dy by dx plus 2 sec squared times by sine x over cos x. Oh, we can just write it like that. So sine x over cos x we can write as tan x sec squared x y equals cos cubed, cos to the power 4 divided by cos. So just looking at this bit here is cos cubed. If I then multiply by sec squared, that's like dividing by cos squared. So that's going to be just cos x. Right, now let's see if we can simplify this any further. What we can notice is that you've got your function y here. Let's say that's the first function. in the derivative, because we know when we times by the integrating factor, we're going to be able to write this in the form of d by dx of some product. So I'm just trying to figure out what that product is. So let's say this is our first function. This is the derivative of the first one. So this one should be our second function. Let's just see if it works. If that's our second function and we differentiate it, that's going to be 2 sec x, but you times by the derivative of sec as well, which is tan x. Right, so sec squared x, let's just differentiate this on the side here just to make sure. So that's going to be 2 sec x, but you also have to multiply by the derivative of sec, which is sec tan. So this differentiates to that, which is the same as that. So this is the derivative of the second function. So if we write the product down, first function, second function, that's just y sec squared x. So we've seen that if you multiply by the integrating factor, which is sec squared, it becomes in a form where you can then write it like this. So that's equal to cos x. We can now integrate both sides with respect to x. If we integrate the left hand side, integrating with respect to x is the inverse of differentiating with respect to x. So they cancel out and you're left with y sec squared x. The right hand side, we're integrating cos x with respect to x, and we can work out what this is then. Y sec squared x equals, sine differentiates to give cos, so that's going to be sine x plus c. We can now try and write this in a bit of a neater way. If we divide through by sec squared, we get sine x cos squared x, because sine x over sec squared is the same as sine x cos squared x, plus c cos squared x. We can factorize the cos squared out, so it becomes cos y equals cos squared x bracket sine x plus c. That's our general solution. So what did we do? We had our differential equation. We made sure you first put it into the correct form, because it has to be in this form for you to use this method. We found the integrating factor. We then multiplied the whole equation with the integrating factor, and then went to solve it by integrating. Right, so steps. You need to make sure that it's in the correct form. So basically there should be nothing next to the dy by dx. Second step is the integrating factor. So that's e to the power of the integral of px dx. Okay, so if this was on this, px is the thing next to the y. After you've rearranged it, so there's nothing next to the dy by dx, you find the integrating factor. And then you rewrite it. First you multiply the whole equation with the integrating factor. So multiply the ODE by the integrating factor. And then after that you use the differentiation product rule, but in like backwards. And what you should end up getting is d by dx of some product of two functions. One of them will be y is equal to whatever is on the right hand side. And then you can solve it by integrating both sides. Okay, your turn now. So have a go at this. Find the general solution of this. Pause the video, have a go. Right, first thing you want to do is divide by x to get into the correct form. In this case, your px, the function next to the y, is 1 over x, so your integrating factor is going to be e to the integral of 1 over x dx, which is e to the ln x, and so that's just going to be x. Our integrating factor is x, so we multiply this equation by x then, so x dy by dx plus y equals x cos x. So the left hand side, you notice that this is a function, the derivative of it is 1, so it's the derivative of xy equals x cos x. So xy, if we integrate both sides, xy is going to be equal to the integral of x cos x dx. We can do a quick table method here. We're going to differentiate the x's. And integrate the cos. Okay, and so that's going to be xy equals x sine x. If we integrate sine x, that is minus cos x. So that's going to be plus minus, so that becomes plus cos x. So y equals, dividing by x, sine x plus cos x. There should be a plus c on the end. Over x plus c over x. Again, I've made an error. When I divided by x in this stage, that should have been cos x over x. So if I divide by, there's no x here then. When I multiply by the x integrating factor, no x here, no x here. So that's just going to be sine x plus c. And so the answer is sine x over x plus c over x. No need for integration by parts. Right, let's try another one. So imagine we want to solve the ODE x cubed dy by dx minus x squared y equals 1, given that y equals 1 at x equals 1. So when x is 1, y is 1. So it's asking for a particular solution. It's a first order ODE. First thing you want to do is make sure it's in the correct form. Actually check if you can do the reverse product rule straight away. Well, x squared is not the direct derivative of x cubed, so we need to find the integrating factor. Before we can do that, we need to make sure the equation is in the correct form. So what do? Divide by x cubed. So dy by dx equals minus 1 over xy equals 1 over x cubed. So the integrating factor is going to be e to the integral of minus 1 over x dx, which is e to the minus ln x, which is e to the ln x to the power of minus 1, which is 1 over x. So that's our integrating factor. we're going to multiply our whole equation by that, so we get 1 over x dy by dx minus 1 over x squared y equals 1 over x cubed times 1 over x is 1 over x to the power of 4. So if you notice now, you've got y dy by dx, so the derivative of y and the other function in the product is 1 over x. If you differentiate 1 over x, you get minus 1 over x squared, so that works. And that's equal to 1 over x to the power of 4. We now integrate both sides with respect to x. So y over x equals, if we integrate this, we're going to make it into x to the power of minus 4. So that's going to become x to the power of minus 3 over minus 3 plus c. So y equals x to the power of minus 2 is a minus and over 3 plus cx. If we tidy that up a bit, that's y equals minus 1 over 3x squared plus cx. Now, we are told to find the solution given that y equals 1 at x equals 1. So we need to find a particular solution. This is our general solution. To find the particular solution, we're going to substitute those values in. So when y is 1, x is 1. So that's going to be minus 1 over 3 plus c. So 3 equals minus 1 plus 3c. So 3c equals 4. C equals 4 over 3. So our particular solution is going to be what we have above, but we can replace the c now. There we go, that's our particular solution. And that's how you solve a first order ODE. So what we looked at in this video is that you can have very basic ordinary differential equations like this. Well, it's obvious here what you need to do to find what y is. And you can then, once you know what y is, you can draw a sketch of what the family of solutions look like. We've seen that if you have a first order ODE, you can check to see if you can use the product rule in reverse. And the main thing, the biggest thing, is to be able to solve first order ODEs of this form, for which you need to first of all find the integrating factor, which is given by e to the integral of px dx, where p is the function next to the y. And you also have to make sure that there's no function next to the dy by dx. Okay, once you know your integrating factor, multiply the equation by that, and it will become in a form where you can use a product rule in reverse. We've seen that if you're given boundary conditions, so like x equals 1, when x equals 1, y equals 1, you can then go on to find what the constants are. So now you can complete exercise 7a and 7b from the textbook, if you haven't already. And then in the next session, you'll look at second order ordinary differential equations.